Hey guys, so today we are going to talk about the rest of chapter 15, which has to do with molecular orbital, thermo and kinetics, and Diels-Alder, my favorite topic to teach. So before we dive into the remainder of chapter 15, I'm gonna kind of give you a glimpse of what this unit holds. Oh, didn't mean to do that. Just give me 1 second. Okay. So chapter 15, chapter 16, and chapter 17, as well as chapter 14. Okay. So we've already done chapter 14, which is ethers, epoxides, just mechanisms, more reactions, pretty standard stuff. Chapter 15 is when you get into new material. For the first time, you are learning about conjugated systems, which we did last week. And you need to know that material before I talk about this week's material. So if you haven't already, go ahead and watch the previous video on that. We are also learning about molecular orbitals for this unit, as well as thermo and kinetic, and lastly Diels-Alders. Diels-Alder. Okay, so chapter 16 covers aromaticity, so all the rules on what it means for a molecule to be aromatic, and this includes aromatic, non-aromatic, and anti-aromatic. So you will have to distinguish between these three when given a set of molecules. You have to identify if it's aromatic, non-aromatic, or anti-aromatic based on the 4 different rules of aromaticity. But we will talk about that more in detail next week. And then lastly, chapter 17, we have Benzene Reactions, or aromatic reactions. We have EAS and NAS. Directors. Directors are your ortho, para, and meta. So I'm sure you guys have briefly heard about it so far in exam 1. You've seen a lot of examples where para NMR was utilized a lot. That gives you additional information on how to form your molecule. And then we also briefly talk about basicity of nitrogens. Alright, so that's just a quick overview of this whole unit. I didn't mention it last week, but hopefully this week you guys will get a better understanding on how to prepare for this next exam, especially if the exam 1 did not work out so well, and especially considering you guys only have 2 exams this semester. Alright, so let's get started with molecular orbital. Alright, so I am going to use this example to talk about this concept, okay? But before we get into that, I want to briefly mention, well, the proper name for this is 1,3-butadiene. Okay, this is a standard example that you will almost always see when learning about molecular orbitals because it's the easiest to showcase. Okay, so the first thing that you need to do, well, there's two things that you need to figure out. The first one is number of pi electrons. Okay, so we have to figure that out, and then second, we have to figure out the number of carbons in conjugation. Okay, yeah, so you have to count all the carbons that are able to conjugate in the given structure. Okay, so let's go ahead and fill this out. So number of pi bonds. Okay, so sorry, not pi bonds, pi electrons. So how many, or where are my pi electrons? Okay, so each double bond is 2 pi electrons, and a negative charge is also 2 pi electrons because it's essentially a lone pair. A positive charge is 0 pi electrons, and a radical is 1 pi electron. Alright, and then other definitions you should also know is what HOMO stands for and what LUMO stands for. Okay, HOMO stands for highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. Okay, so knowing what that stands for is very important on answering the questions. Alright, so for this example, let's count all of our pi electrons. So I see 2 double bonds, which means 2 pi electrons per double bond, giving us a total of 4 pi electrons. And then I see 1, 2, 3, 4. 4 carbons are in conjugation, so we also have 4 number of carbons. Okay, now once we have that information, we can go ahead and draw our molecular orbital. Okay, so let me try to zoom out a little bit. Okay, so you won't be asked to draw the molecular orbital, but this is a way of understanding where everything is coming from. So the number of carbons will tell you how many pi levels there are. This is either known as pi 1 or n1, doesn't matter. So I'll refer to as pi 2, pi 3, pi 4. Okay. Now the reason why I only have 4 is because I have 4 carbons in conjugation. Okay. And next to each of my energy levels, I have 4 orbitals. Alright. So the number of carbons will tell me how many energy levels, as well as how many pi bonds there are. Okay. So these pi bonds look like figure 8s, so I'm going to draw 4 of them. In each energy level. Alright, so let me redraw these so that's more straight. Alright, so that's not perfect, but yeah. Alright, So next thing we want to look at is nodes. So nodes stand for anywhere there is a difference in positive and negative, okay? So don't get this formula to find nodes confused with the formula from the past unit, which was n plus 1, but here it's going to be n minus 1, where n equals energy level, or pi level. Okay, so n1 would be 1 minus 1 equals 0 nodes, 2 minus 1 equals 1 node, 3 minus 1 equals 2 nodes, and then 4 minus 1 equals 3 nodes. Okay, so these are our nodes. This is our energy levels. And these are our pi electrons. Alright. So now we are going to fill in our orbitals using our nodes. So 0 nodes means 0 dotted lines that I have to draw symmetrically to show a difference in charge. So I'm going to fill in all of these without any change in charge, okay? So a little caveat is this can be written as that. It's the same thing. So if it's shaded, it's going to be positive, and if it's empty, if it's white, it's going to be negative, okay? So in this case, I'm going to shade it. So one node means I'm going to place a dotted line as symmetrically as possible. So where that dotted line is, that's where I have to flip my charges. So instead of it being right here, it's going to go down below. And then 2 nodes, I have to place it in the most symmetrical spot. So 1, 2, 1. It is the most symmetrical, and then at top, and then 3 just between all of them. Okay, if this doesn't make too much sense, don't worry about it. It's a new concept. Hopefully it would start clicking in once you do more practice problems and see more examples on it. So after we filled out our molecular orbitals, now we have to fill out our electrons right on the right. Okay, so we have 4 pi electrons, right? Now if you guys remember, each orbital can only hold how many electrons? That's right, 2 electrons. So we are going to place 1 up arrow and 1 down arrow, okay? And now after we place, then if it's full, we have to go on to the next energy level. 1 up arrow, 1 down arrow. Okay, now we have 4 pi electrons. We used all of our pi electrons. We took care of the 4 carbons. We drew our energy levels. Now all there is to do is figure out which one is our HOMO and which one is our LUMO. Now, of the 2 occupied right here, HOMO has to be the highest one. So it's going to be N2 or pi 2. So this is our HOMO because this is our highest orbital that is occupied by electrons. And then LUMO is our lowest unoccupied molecular orbital. So it's going to be this one. Okay? Alright. I will do another example, but before I do that, I want to explain a unique situation that you might have to deal with. sometimes they will ask you, or they will tell you that these electrons are getting excited either through UV/light, and what this means is it excites the last electron to the next orbital. Okay, so if I have the exact same 1,3-butadiene, but it tells me one of my photons is getting, or one of my electrons is getting excited through UV or photon energy, it's going to look like this. I have 1, 1, and then 3, and then instead of drawing it right there, it's going to be drawn right here. All right. Now, if they were to ask me HOMO and LUMO for this would be my HOMO, because this orbital is still occupied by a single electron. Now, it doesn't have to be fully occupied by both electrons. As long as it has at least one, it's considered occupied. And then LUMO is still, there's only one unoccupied orbital here, but if there was another orbital above it, it would obviously be the lower energy level one. Alright, so this is only when it gets excited through UV or light. It has specific wording, so I would make sure you watch out for that wording. Alright. So sometimes they will also mention bonding and non-bonding. So bonding, in an even number of carbons, bonding are going to be the bottom two. It's going to be symmetrical. So these are your bonding ones, and these are your non-bonding ones. Alright, so example number 2. I'm going to draw right here. Alright, so I want you guys to tell me the exact same information I wrote above. So number of pi electrons, number of carbons in conjugation, and then draw the molecular orbital and tell me HOMO and LUMO. Okay, so go ahead and pause the video right here while I complete the answer, while you guys also try to attempt it. Alright, so hopefully you guys have solved it. If not, keep continuing solving it. If you have so, I'm going to show you guys the answer now. So this time we have 5 carbons but 6 pi electrons, because we have 2 double bonds and a lone pair, or a negative charge, which is essentially a lone pair. So we have 6 pi electrons there, 5 carbons in conjugation. That means we have 5 energy levels. And 5 energy levels, but we also have 5 pi bonds. And nodes are just 0, 1, 2, 3, 4. So again, one node. So when we have an odd number of carbons, it's going to be a little bit weird with nodes, because you can actually also draw a dotted line through a pi bond, and that would essentially not get any positive or negative charges. So we did so in N2, or N2, 3, and 4, where we drew dotted lines. So this still showcases a change in negative and positive. So hopefully you guys can see that. I'll zoom in a little bit right here. And then we had 6 pi electrons, so we have up, down, up, down, up, down. So on the third energy level, that's our highest occupied molecular orbital. So that's our HOMO, and our lowest unoccupied is our energy level 4. Now this bonding, non-bonding, and anti-bonding, I'm not sure how much you have to know about it, but essentially when we have an odd number of carbons, or energy levels rather, your bottom two, or your bottom half, are going to be your bonding, your middle is going to be non-bonding, and your top half is going to be anti-bonding. And I'll show this for even. So for even, your bottom half are going to be bonding and your top half are going to be non-bonding. So only when you have sorry, I did this wrong. So this should be anti-bonding. Okay, so top half is always considered anti-bonding, and the middle, and that's only for odd, is going to be non. Okay? Alright, so typical questions that you might get are, what energy level is HOMO in, what energy level is LUMO in, how many pi electrons are in HOMO and how many pi electrons are in LUMO, which energy levels are in the bonding, non-bonding, or anti-bonding, any number of those questions. Alright, let's move on to thermodynamics and kinetics. So I'm going to use this typical example. As you'll probably use it a lot. And then this is going to undergo HBr. Again, something common that they will probably ask you. Now, HBr, so let's draw 2 of them. Or actually, HBr. And then, so how do we know if this HBr is kinetic or thermo? Okay, so usually they will give you temperature. So -40 degrees will mean that it's kinetic, okay? And the reason why you can tell it's kinetic is because kinetic has the letter K, which stands for cold. It also has a 1-2 pattern, and it has the most stable carbocation. Okay? So if you guys remember HBr, it breaks a double bond, it adds bromine onto the more substituted products. Okay? So on our original structure, you want to label all of your double bond degree, yeah. So secondary, tertiary, primary. Now of these 4 positions, the top double bond has a tertiary position, and that would be the most stable carbocation. So we are going to break that double bond and add our carbocation. So double bond here. We broke this double bond, we replace it with the carbocation here, and this bromine will then attack this positive charge. So that's the first step, and the second step is adding the bromine on. Now let's do thermo. Let me zoom out a little bit. Thermo, again, we're going to use the same structure. HBr, same reagent, but the only difference is it's now going to use a higher temperature. For example, 80 degrees Celsius. So thermo or thermodynamic is going to be hot because of the H in thermo, and it has a 1,4 pattern, and it has the most stable alkene. Okay, so that means we want our double bond to have the most number of substituents. Whereas in kinetic, we want our carbocation to have the most number of substituents. Okay, so this has an extra step. This also has resonance. So let's number these again. It should be the same. So you start off thermo just like how you would with kinetic. You still break one double bond and leave that carbocation right there. Okay, so that's the first step. Number one, number two. But step 2 from here is resonance. Okay, you have to resonate that carbocation with the double bond. And the reason why we do this is to get our double bond in the most substituted position we can get. And then step 3 is bromine attacking. Alright, so hopefully the most stable carbocation and the most stable alkene makes sense, but if it doesn't, I'll go over these again. So this carbocation is 1, 2, 3. So it's in a tertiary position, and that's the most stable position we can get on this molecule. For thermo, the most stable alkene. So this double bond is in 1, 2, 3. So it's also tri-substituted position. Okay, whereas here it was only 1, 2. That's why we resonated to go from a secondary to a tertiary position. And then the 1, 2, 1, 4, those numbers are coming from here. So if we label 1, 2, 3, 4, 1, 2, 3, 4, our starting compound and our starting carbon and ending carbon that has the bromine on it should be 1 and 2. So in this case, it's 1 and 2. 1, 2. Here we have 1, 2, 3, 4. So 1 and 4. Okay? So that's where the numbers are coming from. So if you always want to double check yourself, if you did it right or wrong, this is a good way to check. Okay? So that is essentially the gist of thermo and kinetics. It's pretty straightforward. You just have to be careful about the temperature, because this is the only thing that will differentiate between kinetic and thermal. And then here's the most important differences between the two. Alright? So fairly straightforward. Now lastly, we are going to talk about Diels-Alder. Alright, so Diels-Alder. So Diels-Alder, it's kind of like a puzzle piece. We have two puzzle pieces together, and you're trying to put together a whole. So we have our diene, and we have our dienophile. Okay? Our diene looks like this, and our dienophile looks like that. Okay? And this, both of these combined will give us our product. Now, regardless of what is on your diene and what is on your dienophile, your product should always have this molecule included. Now, there might be something else added to this molecule, but it will always have that template on it. Now, if I had more colors, I would show you where everything is bonded, but for now, I'm just going to use arrows. So one of the double bonds is going to come this way to form another bond in the ring. This double bond is going to come here to form the double bond that we see in our product. This double bond in our dienophile is going to come and form the other part of the ring right here. And then lastly, this remaining double bond is going to come and fill in our third bond that we need. Okay? If I had more colors to show you guys, it would be a lot more clearer, but for now, that's the idea of it. So stereochemistry on our product depends on two different things. So let's talk about stereochemistry on our diene first. Now keep in mind that this is relative, as in either the way I am teaching you guys could be the enantiomer of the way someone else will teach you. So as long as you stick to one side or the other, you should be good. So if you have any groups on these two carbons that's pointing this way, these are going to be wedges. And if you have any groups that are pointing outward, either straight above or straight below, these are going to be dashes. Okay? So that's our stereochemistry for our diene. For our dienophile, it depends if you are endo or exo. Okay? Endo means that it is a electron withdrawing group. An electron withdrawing group, sorry, let me use a different color. Endo equals electron withdrawing group, and electron withdrawing groups are going to be dashes because it has the D in endo. That's a good way for you guys to remember. So it has a dash for stereochemistry, and examples of molecules that fit electron withdrawing groups. Now, this list is something you should also keep in mind when you start to learn about activators and deactivators in chapter 17. So CN, NO2, any of the carbonyls. This means ketone, aldehyde, ester, carboxylic acid, amide, any number of those things. Acid chloride, all right? And then exo are electron donating groups such as OH, NH2, OR, CF3, and CH3, a methyl group. Okay? And then exo, if endo is dash, exo is going to be wedge. Alright, so that's our stereochemistry explained on 4 carbons. So to review, let's draw our product again. These 2 carbons have no stereochemistry. Do you guys know why? Because they are on double bonds. Double bonds do not have wedges or dashes. It's going to force all bonds to be on the plane. Now these two carbons are dependent on the orientation the groups are facing. Whether it's pointing outward or inward, that's where our stereochemistry is coming from, on our diene. And then lastly, these two depends if our groups are electron withdrawing or electron donating. So I would memorize this list for now. Eventually you'll be able to distinguish whether a molecule is withdrawing or donating without having to recall any information. Okay. Now there is another way that you could do. You could assign stereochemistry and get Diels-Alder using positive and minuses. I personally feel this is a shorter way. Positive and minuses are they take longer, in my opinion, and it's very easy to make mistakes and get stereochemistry wrong. So again, this is just one side of the enantiomer. All of these wedges and dashes and endo and exo groups can easily be flipped, and that would be the enantiomer version of what I'm telling you. But from what I've seen, this is the more accepted way, but it really doesn't matter. Just stick to one way or the other and just continue with it. Now, a few exceptions. Or weird ones are when they give you this pentagon looking thing. Your product should be, you would still always have your cyclohexene, but instead you now have oxygen in the middle with wedges coming out of the page. Okay? And then this also looks the same as drawing it like this. Okay? Exact same thing. Oh, oops. Let me fix that. There you go. So either way, that's the exact same answer. Don't worry about how it looks. Don't get startled. Now, 2 more things, and we will be done with Diels-Alders and Chapter 15. So there is a rule where you cannot have your substituents in a 1-3 fashion. Let me show you what I mean. So let me just show you the products. You cannot have a 1-3 substituents, because when you remember when you draw cyclohexanes in a chair conformation, those 1,3 diaxial interactions cause a lot of steric hindrance that prevents you from having stability in the molecule. So instead, when this NO2 is pointing downward because it was probably given this way, so we have to flip our NO2 to look like this, where our product will have NO2 on the top side, right next to our substituents. So it's actually 1, 2. So we either want 1, 2 or 1, 4, not 1, 3, okay? So 1, 3 is bad for steric hindrance when we convert it to chair conformation. Lastly, your dienes are not always going to be in a S-cis formation. S-cis is this formation right here, S-cis. It's cis because the double bonds are facing the same direction. So sometimes they are slanted in a S-trans formation, such as this. Okay, so these double bonds are in a S-trans formation. So what you have to do is you have to rotate or reflect one side to match the other to get into that. So this is currently in the S-trans, and we want it to get into the S-cis. Okay, you can do this by drawing a dotted line down the middle like this, reflect it, and have everything exactly the same as side 1 and side 2. So if you flip side 1 and side 2, they should match up. Now I just put the double bond on the other side for convenient reasons. So when you flip this new side, so this new side is what you should see in your typical diene formation. So it looks like this. Okay. And that's your S-cis. And now from here, a dienophile will be ready and willing to attack. All right? So from here, we have our dienophile, which can make our products. All right, well, there you have it. That should be the end of dienes. Diels-Alders. So lastly, I will leave off with some example Diels-Alder problems. Alright, so go ahead and do those problems. I would pause the video, so in a few seconds I'm gonna have the answers on the screen. Alright, well there you have it. Here are the answers.